Hi everyone, it's John again. Just going over the next worksheet. So I hope this helps. So it looks like this week is going to be molarity, as well as a little bit of redox at the end. But we'll work through each of these questions. All right. So number one, it says when a solution is aqueous, what is the solvent? So when something is an aqueous solution, or it's in aqueous phase, the solvent is water. Um, yeah. So if you see aqueous, assume it's dissolved in water. Two, we have dilution questions. It says if water is added to 50 milliliters of NaOH, resulting in a doubling of the total volume, what is the new molarity? Got it. So the way you want to do this, a few ways you can think about it. So you can think of, this is what I'm going to do it. M1 V1 equals M2 V2, and we can find the new molarity as a function of the initial molarity. Or you can kind of think about it intuitively, where if you have something with some amount of stuff in it, and you double the amount of stuff it's dissolved in, you're going to have half the amount of stuff per unit space, right? If you had a box, a 1 by 1 box full of marbles, and then you double the box size, then there's about half as many marbles per space in the box. Um, so I'm going to use M1V1 equals M2V2. M1V1 equals M2V2. Now the 50 kind of actually doesn't really make a difference here. Um, so it says if the water is added to 50 milliliters of NaOH, so I assume some sort of NaOH solution with some molarity, um, we just know that the volume doubles. So it apparently you added 50 milliliters, but that doesn't really matter for this question, right? Because we're trying to find molarity, not volume. So what I do know from what I'm told, is that the second volume is equal to twice the first volume. Now what I can do is plug this into the equation. I get M1 times V1 is equal to M2 times 2V2, right? Just by substitution, because I know the second volume is twice the first. As you'll notice too throughout these videos, I like to put a lot of things in an algebraic context as well, because I think it makes it easier to do the math, see the relationships, and if you end up taking physics or other things, you're going to see the same type of um, ideas portrayed in the same ways where you're working in terms of variables and trying to relate things. So now since I plugged it in, if I divide both sides by V1, these both cancel out. Um, and then I get M1 is equal to 2M2, or the initial molarity is twice the second molarity. So you can end here. I'm going to make it very explicit, where the second molarity, so the second concentration, is equal to 1/2 of the first. I just divide both sides by 2. This is 1/2 times M1. That's the same as M1 divided by 2. I just like writing the 1/2 out front. It makes it very clear to me. And that's it. So you get half, right? If you double the volume, you half the concentration. That's it for that one. For B, it says enough water is added to 3 molar HCl, resulting in the final volume to be triple the initial volume. What is the final molarity of HCl? So we're going to use M1V1 equals M2V2 again. Great. So we start with our equation. Any dilution, you're going to use this always. You see any dilution, you add something with some concentration to something else, dilute it. It's probably something with a dilution. So uh, first we have M1 is equal to 3 molar. Right, so I'll actually make these very clear. M1 equals 3 molar. I'm not going to write the units just to avoid confusion. M2 is something I don't know. It's what I want to solve for. The first volume is something that I also don't know. However, I do know that the final volume is triple the initial volume. So I can say this, V2 is equal to 3V1. If you want to make it really clear, you can say V1, so M1 is the initial concentration. V1 is the initial volume. M2 is the initial, or sorry, final concentration and molarity. And then actually it's not always, it can vary a little bit. And then V2 is the final volume. Right? So one indicating initial, two indicating final. If you like it better, you could say VI and VF. If you like it better, you could say V naught and then VF or whatever. That's a common physics notation. The 0 for initial state, F for final. Do whatever you want, notate however you want, whatever makes it clear. All right. They all mean the same thing. So we go ahead and we have all these numbers. So we're just going to plug them in. So 3 times V1 is equal to, and you could also put 1/3 V2, that's going to be equivalent, is equal to M2 times 3V1. So notice how I substituted V2 here in for 3V1 in the equation. You could do the other way, it doesn't matter. You could do V1 is equal to 1/3 V2, as I said, won't change the math at all. And then we're going to get M2. When you do some algebra, divide both sides by V1 and 3, you get 1. So it's 1 molar. And that's it. Why is it a molar? Because our other concentration was in units of molarity. Molar means molarity, by the way. All right. 3, it says in the following reaction, what is the solvent? Well, they're all aqueous. So the solvent is water. Great. Again, if you see anything aqueous, you assume it's being done in water. If the reaction above goes to completion, or reactions are fully consumed, what is the solute? So the solute is the thing that is dissolved in solution. Now, I think something that makes this more clear is they're saying it goes to completion, so you have no more reactants. So assume that these are not in the beaker anymore. Otherwise, you have two answers. So assume these are not in the beaker anymore because they're gone. They're completely reacted. You have a solid and you have something dissolved in it. The solute is the thing that's dissolved. So it's that one. Something that's solid that precipitates out from a solution or forms because of a reaction in solution as a precipitate. But the solute is the thing that is dissolved. It has to be dissolved or it's not a solute. 5, it says, what are the molarities of the following solutes when dissolved in water? So we have that many grams of CH3 to CO and 525 milliliters of solution. So to find the concentration in molarity, you get the molarity is equal to the moles of solute over liters of solution. So what you have to do is first find moles, right? You may have been shown a way where they just convert straight across using fractions. That's okay too. I like to put things in the context of a few formulas in case it's not clear of how you go from one step to the other. So molarity is related to moles and liters. So we need the moles, right, of CH3 to CO. So what do? We convert it using the molar mass, which I'm going to look up. If you were to do this on a test, well, you'd be caught for cheating. So don't do that on a test. Don't look it up on the internet. You're going to have to, on the test, you're actually going to have to look up on the periodic table. So it's 58, about 58.1. So first we can go ahead and convert this. Oops. No, that's right. Convert this to moles. So this is about 58.1 grams of that stuff for every 1 mole. Then you have your unit of moles, right? So what you can do here, you can either take this and plug in to, yeah, Actually, I'm going to do that because it may make it easier if you get stuck on some different problems. I'm going to plug into the equation. Let's just keep with that. So if you plug this or divide it, it's going to be about equal to 1. It's not actually 1. It's close enough. Um, it's about 1. It's probably like 0.98 or something like that. All right. So then the next thing that we can do is plug this in the equation. Yeah, it's correct. 0.99. Um, then we plug this in. We get molarity is equal to 0.99 moles. Keep in mind your units. This is milliliters. This is liters. So convert. This is 0.25, 525, sorry, liters. And then you get 1.89 molar. That's it. You can do it fractionally too, right? If you want to just go across, you could say, well, times I have a unit of volume on the bottom. Oh, but then that needs to be in liters. So you convert to liters, right? That's also okay. Um, they're mathematically the same. It's just whatever makes it easiest for you. B says 18.5 milliliters of C3H5OH3. And then you have the density in 375 milliliters of solution. What we have to do here is find the grams, right? We have to convert from milliliters of our thing to grams of our thing to moles of our thing to molarity of our thing, right? So this one I'm actually going to do in fractional format so that way you can see both, and also just because it's going to be faster. Again, if you get stuck, if you're like, well, how do I go to molarity? Well, you need moles and liters. So that's again where these equations can be helpful if you get stuck on a problem. Don't just memorize, plugging in stuff. Actually understand where it's coming from. So we have 18.5 milliliters. I'm not going to write this whole thing down just for the sake of time. We have, oops, a density of 1.26 grams per 1 milliliter. Again, why am I doing this? So that I can eventually get moles. So I can use that for molarity. Then I have, so what's the molar mass of that? 36 plus 5, 41. 41 plus 17 times 30, 51, like 92-ish per 1 mole. And then we want our liters on the bottom, or unit volume. That's not in liters, so we convert. And then we get some answer. 1 sec. It's going to be 0.674 molar. That's it. 6, it says, what is the concentration of Cl minus in a 0.100 molar solution of aqueous ferric or ferrous, sorry, chloride? Okay, so the first thing you have to know is, what is ferrous chloride? Ferrous chloride is iron 2. So ferrous chloride is, or I should say ferrous is iron 2. And then, so ferrous chloride is FeCl2 because Cl has a -1, and then the ferrous is implies iron 2 or 2 plus oxidation state. What is the concentration in a 0.1 molar solution? Well, this isn't a 2-to-1 ratio, right? There are 2 chloride ions for every 1 FeCl2. So the molarity is twice as much. But you may be thinking, well, why am I allowed to do that? I thought I always had to relate things to moles first before I could do anything stoichiometrically or any of that kind of mumbo jumbo, right? Well, they're in a solution. The solution is at a constant volume, right? Because the solution has a constant volume, this for molarity, you're allowed to just compare the molarities because they're directly related to moles and the volume is not changing. So looking in terms of molarity, in a solution at a constant volume, you can just do the same stoichiometry with as you did with moles. So you can say for every, oops, so we start with 1 molar FeCl2. Then for every 1 molar of FeCl2, I have 2 molar chloride ions. And it's because, again, the volume is constant. I cannot stress that enough. If you're mixing stuff, if you're changing the volume of things from one to another, you can't just do this. So please keep that in mind. Constant volume is important because later on you'll see molarities of different things that you're adding together, and you will have to convert those to moles first. You cannot keep things in terms of molarity because you're adding different volumes of different things together. All right. 7, it says an excess of aluminum foil is allowed to react with 225 milliliters of HCl. That's aqueous. Okay, that contains 18% HCl by mass. What is the mass of H2 produced? Regarding this question, what missing piece of numerical information is necessary in order to solve the answer? Well, what would you need, right, for this reaction? So if you're looking at the question, they give you some aluminum foil that's in excess, right? So we don't really have to worry about how much aluminum foil there is or anything like that, right? So A is gone, AL by mass, because it's in excess. We have 225 milliliters of aqueous hydrochloric acid, and it's 18% HCl by mass. Now, you can't find how much HCl is in here, right? If you want to figure out how much H2 is produced, if you write the chemical equation, you need the moles of HCl, right, that you have. So what's the problem? The problem is you have HCl by mass. You're given a unit of volume. You can't just take 0.18 and multiply it by 225. They're not the same thing, right? It's not by volume, it's by mass. So if you have the volume of HCl, one way you could solve this is if they gave you the density of the solution. Well, why does that help? Because if they gave you the density of the solution, then you can find the mass of the solution. Then you can find the moles, or sorry, mass of HCl, and then you can find the moles of HCl, right? Similarly, if you have the molarity, then you can just find the moles of HCl. So there's 2 answers here. All right. So again, these are just 2 ways that we could get moles of HCl in some way and relate it to the chemical reaction, or in the chemical reaction to moles of H2 gas that form. 8 says, in order to make an aqueous solution more concentrated or a higher molarity, what would one need to do? Add water. So as we discussed before, when you add stuff, you dilute it. Unless you're adding a more concentrated version of that thing. So, but in general, if you're adding something that's pure, you're diluting it, right? So you have some solution in water, you add pure water, you're diluting. So what would you need to do? It says add water, that dilutes it, as we just said. It says add solvent. The solvent's water. So that's also out. It's the same as A. C, it says remove the solute from the solution. Well, if you remove solute, this decreases moles, which then decreases molarity. So that's out. If you remove solvent, then if you look at this equation, if you're removing solvent, you're making the volume of solution smaller. If you're dividing by a smaller number, you get a bigger number, right? 4 divided by 2 is 2. 4 divided by 1, a smaller number, is 4. So this is the answer. Remove some solvent from the solution, you can boil it off. And then you get something more concentrated. Remove solution from the solution. If you remove solution from the solution, it's the same concentration, right? You're not doing anything. You're just kind of taking some of it out and moving it. Yeah. All right. Because again, these are concentration things. So if you were to think of it in terms of how many moles you have in the solution, you would lose moles in the solution and volume of water, but the concentration, per unit volume is going to be the same in what you take out. Which solution has the greatest concentration of sulfate ions? So essentially this question kind of boils down to which one is the most soluble and which one will give the highest concentration. So let's see. Solubility rules. So sulfates, where is it? Sulfates are soluble, except those of calcium, strontium, and barium. Okay, so we're going to assume all sulfates are soluble, right? Completely soluble. Let's also assume, for the sake of argument, that these fully dissolve. Kind of the one I'm looking at is H2SO4. If you don't know why, it's okay. But for the sake of argument, let's assume that these completely dissolve, right? So this produces two SO4s. For one molecule. This is one SO4 for one molecule. This one is three SO4s for three molecules, or for one molecule. Just like we did before, we're going to go ahead and relate molarity, just as I think we did number 5 or something, number 6, right? Where we're just going to multiply by the molarity of the molecule. So the molarity of the molecule for A is going to be 0.075 molar. Oh, why did I put 2 here? Sorry, that's totally wrong. That should be a 1. There's only 1 here. So that's 0.075. This is 0.15 molar of sulfate. This last one produces 3 sulfates. So 3 times 0.08 is going to yield 0.24 molar. So the answer is C. That one's the highest. And again, these are in a constant volume, which is why you're allowed to do this. Do not do this when you get into titrations. I promise you'll get stuff wrong. 10, it says 25 milliliters of HCl is added to 50 mils of 0.75 strontium hydroxide. What must the concentration of the HCl solution be in order to completely neutralize the strontium hydroxide solution? So if you have this is a strong acid, a strong base, presumably strontium. That's slightly soluble. Okay. So for the sake of argument, again, when we're saying completely neutralize, that means completely convert all of the strontium hydroxide to water and a salt. So strontium chloride. Strontium hydroxide is not fully soluble, but again, we're going to assume you're dissolving everything. It also makes sense when you learn Le Chatelier's principle and you're pushing equilibrium around, that it could fully dissolve. So for the sake of argument, again, even though on your solubility sheet, it says that it's not fully soluble, we're going to assume all of it dissolves. It should fully dissolve based on principles that I don't think you have learned yet. So this is where we need to compare the moles to one another. So how many moles of hydroxide? And let me actually write the equation first. So for every 2 moles of HCl plus strontium hydroxide, we get strontium chloride and water. That is the balanced chemical equation. So you can clearly see here, we need 2 moles of HCl for every 1 mole of strontium hydroxide. And it makes sense because the H plus pairs up with the O minus, OH minus, and there's 2 OH minuses, right? So you need 2 H pluses, and they form water. So first we have to figure out how many moles of strontium hydroxide we have. So 0.5 molar strontium hydroxide. Converting this to moles. So we have 50 milliliters of solution. I'm going to say 1 mole per 1 liter. We have 50 milliliters, which is 0.05 liters. I'm not going to do the double conversion because I'm going to run out of space. If you need to, that's okay, but I will not. Now this tells me how many moles of strontium hydroxide I have. Now with stoichiometry, you can tell that for every 1 mole of strontium hydroxide, I have 2 moles of hydroxide, right? Because there's 2 hydroxides per 1 molecule. And then mole is just a scale up factor, right? By Avogadro's number. It's like 1 egg and 2 eggs versus 1 dozen egg and 2 dozen eggs. If you saw the last videos and the analogy I made. Okay. And then we're going to convert from moles of hydroxide to moles of H plus or HCl. So for every 1 mole of hydroxide, I need to use, well, actually, I should have just kept this normal stoichiometry. Yeah, I'm thinking in terms of breaking everything down because then you could do a 1-to-1 there. So let's actually remove this. Um, so let's go to moles of HCl. That's what I should have done. Make this shorter. So for every 1 mole of strontium hydroxide, you get 2 moles of HCl, right? Just by stoichiometry. I was doing kind of a extra stoichiometry, which is not needed and is kind of silly for me to do. So we plug this in and we get the moles of HCl that we're going to need. But I want the molarity of the HCl solution. So what do? Well, I divide by how many milliliters I'm using. I'm using 25 milliliters, which is 0.025 liters. And now I have units of HCl divided by liters. Now, if you want to be very, very, very precise with your units, you could say on the beginning liters, because like, what's the difference between these 2 liters, right? Well, this one's a strontium hydroxide solution. This one's a HCl solution. So you could say like that. 1 liter strontium hydroxide solution. Same here. And then this would be of HCl. So they're different units. You just have to keep the context in mind. You can write everything out. I usually don't for the sake of time. When you plug this all in, you're going to get 3.0 molar. That's your answer. Number 11, it says, what is unique about a titration problem? What are common characteristics? So a titration problem, you are mixing an acid and a base together. The common characteristics is typically you are neutralizing. And the moles of H plus or H3O plus and OH minus must be equivalent to neutralize, right? So that's the common problem, common type of thing. Yeah, generally you're doing stoichiometry. 12, it says a sample battery acid is analyzed for its sulfuric acid content. A 1 milliliter sample that weighs 1.239 grams is diluted to 250 mils, and 10 milliliters of this diluted solution requires 32.44 milliliters of that much barium hydroxide for its titration, so to neutralize it. What is the mass percent of H2SO4 in battery acid? So first, we're going to work backwards from barium hydroxide. This is how much barium hydroxide I use. And let's also write the equation out. Like that. That'll be useful in a second. So we have 0.00498 moles of barium hydroxide for every 1 liter of barium hydroxide solution. Then we want to convert this to moles of barium hydroxide, right? So we can relate how many moles of barium hydroxide was used um, to neutralize this sulfuric acid. That's what you always want to do. Convert to moles. Again, this is where we're mixing things. Now we can't just relate the molarities or anything like that. So you're mixing things. I need to figure out how many moles of barium hydroxide I used to neutralize this, right? If you look at our equation, every 1 mole of barium hydroxide neutralizes 1 mole of sulfuric acid. So how many liters of solution did we use? We use 0.3033244 liters. I'm not going to do the conversion on here. And then times, so now we have liters of BaOH2 solution. Then we go ahead and we have moles of barium hydroxide, right? Because the units cancel out for the liters of barium hydroxide solution. Then we can do stoichiometry. So for every 1 mole of barium hydroxide, you get 1 mole, or it reacts with 1 mole of H2SO4. Now we're in moles of H2SO4. Now I want to go to concentration of H2SO4. So this is where it's a little tricky, right? Because we had 10 milliliters of solution from an already diluted solution. So what do? Well, first let's consider the 10 mils. So how many moles was in the 10 mils? Well, let's see. So actually, no, that's correct. Yeah, so we're gonna have to go ahead and do this. We have 0.01 molar, or sorry, liters of the H2SO4 diluted solution over or on top, whoa, under 1. So now we're working in moles of H2SO4 per 0.0 per liters of H2SO4. And keep in mind, this is the diluted solution. So this is not really a unit. This is just to help keep track of what's going on. So we plug this all in. And I get 0.01. And we're not done because this is the diluted solution. So what we do is well, how do we get the original solution? Well, as I just said, it's dilution. So think M1V1 equals M2V2. And we want to work backwards. So we want to find the initial concentration after the second dilution, or before the second dilution. So we don't know what that is. We do know it was 10 milliliters of that solution. Oh, my bad. I actually misread this. So you're taking 10 milliliters of this diluted solution. So they're the same concentration. So this is the concentration of your 250 milliliter solution because you took 10 mils of it. Okay, great. And then we have M1 times V1. So the actual battery, we took 1 milliliter of that. M2 is what we just solved for, 0.0162. And we had a final volume of 250 milliliters, right? We took 1 milliliter, diluted it to 250. Now notice how I'm working units of milliliters here. That's okay. The units cancel out. Just make sure they're in the same unit. So you can use liters, milliliters, it doesn't matter. Make sure there's the same unit though here. In molarity, if you use that equation, do make sure you're using liters though, because that's how it's defined. So that times 250, we get 4.04 molar. Okay, so we're almost done here. Now we can figure out what the mass is of the HCl. So we had that many moles of HCl per 1 liter. We had 1 liter, or sorry, 1 milliliter of solution. Zero, zero, one. So now I have moles of H2SO4, and I want to convert this to grams. I'm going to use the molar mass of H2SO4. And you're going to say, well, why? Because if I want to find mass percent, I have to find the percent contributed, just like we did for previous problems. Mass contributed by sulfuric acid divided by the total mass of whatever it is. So it's 98, about 98, 98.1. So we have 98.1 for every 1 mole. Now we're working in grams of H2SO4 because everything cancels out. And then the last step is I need to divide it by 1.239 grams of battery acid. And we are multiplying by 100% to get a percent here. So then once you do all that, oops, no, that's correct. 0.001 times 98.1 by 1.239. I get 31 point, or yeah, 31.98%. And then that's it. All right, let's go to the next. 13, it says choose the correct statement about the strength of an electrolyte for a given compound. So an electrolyte is something, a solution with ions is really what it is. So ions that conduct electricity. So pure water does not conduct electricity. You need electrolytes in your water to conduct electricity. The things that help conduct it is ions. They help electrons and charge move about in solution. So it says consider all compounds at room temperature and standard atmospheric pressure. Aqueous perchloric acid is a strong electrolyte. So let's see. Um, we're looking, if we're looking for the strongest electrolyte, we're going to see the one, which one gives you the most ions, basically. Air. So air is not a strong electrolyte, so it's not C. Water is not a strong electrolyte. As I just said, pure water doesn't really conduct electricity. I guess you could say it minorly does based on the auto-ionization constant of water, but let's just say it doesn't. And then E, it says stannous carbonate is a strong electrolyte. I actually don't even know what that is. So stannous carbonate is SnCO3. Oh, I didn't know stannous was an element. So the question is it soluble? So we're looking for the most soluble thing here is really what it comes down to. Acetic acid's a weak acid, so it's not a super strong electrolyte. So the question is aqueous perchloric acid or stannous carbonate um, a stronger or dissolves more? Looks like stannous carbonate is actually, let's look at the solubility table. Let's see if they have it on here. So it says carbonates are insoluble. So stannous carbonate will be less soluble than perchloric acid. Perchloric acid's pretty strong acid. So the answer is A. Again, you're just looking for the thing that has the most or dissolves the most, gives you the most ions. For 14, it says complete each of the following as a net ionic equation. If no reaction occurs, state so. Okay, so we're just seeing for the things that are soluble and insoluble. So first we're going to go ahead and write out kind of what pairs up and what doesn't. So the thing that is insoluble should be the calcium. Yeah, calcium carbonate. Because calcium iodine is soluble. Yep, iodides are soluble. So calcium carbonate is a solid. Then the Na and the iodine pair up, right? And if you want to write this as a net ionic equation, you can just cancel out the things right on both sides. Kind of like what we saw with the equations from before. So we have two sodiums on each side, two iodines on each side. And then we get Ca2 plus CO3 2 minus yields CaCO3, and then we're done. B, we're going to do the same thing. So barium sulfate, I believe, is soluble. Nope, all sulfates are soluble except calcium, strontium, and barium. So barium sulfate is going to be the insoluble thing. Good. Then we have sodium sulfate, or sorry, sodium and the sulfur. So sodium sulfide. Let's say sulfides are insoluble, but salts of group 1 cations are soluble. So because the sulfide pairs up with Na, you don't have a solid form from it because anything with sodium is soluble. So the net ionic equation, again, you just kind of cancel some things out. It's going to be barium plus sulfate yields barium sulfate. The next one, I'm going to go through these pretty quickly just because there's so many and they're all kind of the same idea. So we have Na2S and ferric chloride. Well, NaCl is going to go away, right? Because that is soluble. So, yeah, I'm just going to write it out. This is still aqueous. Then we have iron sulfide. Iron sulfide should be insoluble, sorry. Yep, for rule number 5. So FeS is solid. So the net ionic equation is going to end up being S2 minus plus Fe2 plus yield FeS. Iron 2 sulfide. If you're wondering how I know it's a 2 plus, again, you might want to review the oxidation states. Cl has a -1 oxidation state. There's 2 of them. So iron has to be a 2 plus to balance that out and make that neutral. Sodium carbonate and silver 1 nitrate are mixed in solution. All right. So this one you're going to want to know what sodium carbonate is. Sodium carbonate is Na2CO3. CO3 has a -2 charge, so that is something you are going to want to keep in mind. Silver 1 nitrate. You have AgNO3. Nitrate has a -1 charge. That's also soluble. You can write these as like a double replacement first, right? So that can make it easier. That's what I did for C. We have AgCO3 plus NaNO3, and there's going to be 2 of those to balance, and then there's going to be to balance with the sodium, so there has to be 2 of those and then 2 of those. Wait, yeah, so this is Ag2. Oops. So 1 of those. Then we check our solubility rules. Well, I know this one's already aqueous because it's paired up with sodium. And then we check it for silver carbonate. Carbonates are insoluble, and we don't have any exceptions here that are being said. This is solid. So the net ionic is going to be Ag, 2Ag plus carbonate is going to yield Ag2CO3 as a solid. And that's it. Solid magnesium hydroxide reacts with acetic acid in solution. Okay. So solid magnesium hydroxide is just Mg. Oh, sorry, manganese hydroxide, MgOH2. We have acetic acid. Acetic acid is going to be HC, or whoops, no, H3C, COOH. That's right. H3C, COH. It looks like this. You don't have to know what it looks like, but that's what it looks like. So for this one, we're doing an acid-base reaction, not with the hydrogens out here. You're doing it with the ones over here. How do I know? If it's connected to an oxygen, assume things that are connected to carbon. The hydrogens connected to a carbon are not going to be the ones that leave, that do an acid base. So assume that. It's usually the one connected to an oxygen. If not oxygen, it's going to be the nitrogen one. And then we have, can't really explain that until you take organic chemistry. So we have MgOH2, or sorry, Mg paired up with this counter ion. It's going to be O minus. Oops, no, I'll just write it like this. H3CO3. OO. That has a charge of -1 because you're losing one hydrogen. There's two of them. Plus water. Balance this out. There needs to be a 2 there. And then we get our net ionic equation. Well, let's see what's soluble and what's not. Bromide, salts of silver, lead, mercury. So we don't actually. Oh, there it is. Acetates. Acetates are soluble. Okay, so this is magnesium acetate. Go from acetic acid to an acetate when you lose the hydrogen. That's magnesium acetate. So we do have a soluble thing here. So that's aqueous. So the overall net ionic equation is this. OH minus plus H plus yields H2O. So just your standard acid base, because this is aqueous. We're assuming that's aqueous. Oh, wait, it's solid. Oh, wait a second. So if it's solid, we're going to want to keep that together. Actually, we're going to keep this as our answer. Apparently, this is the answer. You can kind of consider the acetic acid dissolving in water. It usually does not. I mean, it does, but not completely dissolve. So we'll keep this as our answer for the net ionic equation. For this last one, it's going to be Na2CO3 again, so sodium carbonate plus HCl. Then we're doing a double replacement, so NaCl plus H2CO3. Okay, so that's the first step. Now, the one thing that actually does happen here is that there's another equation, another reaction, where this carbonic acid turns into CO2 and H2O. So you also have to know that. All right, so the net ionic equation is going to be starting with this Na2CO3 as a solid, right? And then we have H plus. The chlorine is not there because it's on both sides, right? NaCl is aqueous. It's dissolved, solubility rules. And then this turns into CO2 plus H2O plus Na plus. But you do actually have to know this middle reaction happens or you'll get it wrong. So I don't think this is something that will come up on a test. I can't promise, but yeah. Then we have to go ahead and balance it. So we have two NAs on the right. We're gonna need two more hydrogens, and that's it. No, no. The oxygens, yeah, no, there's three oxygens on each side. Okay, so that's it. Number 15 says fill in the chart for the corresponding compound as a strong, weak acid or base. So HI, so H with any of the halogens, with the exception of fluorine, is going to be a strong acid. KOH, because potassium, so also I should say what constitutes a strong acid and a strong base. So a strong acid and a strong base fully dissolve. If they don't fully dissolve, we're going to say it's a weak acid or a weak base. So HI fully dissolves, so it's a strong acid. KOH, based off of your solubility rules, that fully dissolves. So that is a strong base. Then we have methanol. That's a weak acid. It can give off a proton, the H. Why doesn't the OH come off? It's not super clear, again, until you really take organic chem. But if you see an OH connected to carbon stuff, so methyl's a carbon, carbon with three H's, assume that it's a weak acid, not a weak base. Barium hydroxide fully dissolves. It's going to be a strong base based off solubility. HNO2 is a weak acid based off solubility. It's weak. Hydrogen nitrate or nitric acid. That is a strong acid. And then you have acetic, which is a weak acid. Going on to the next one, it says, which of the following aqueous compounds is a strong acid? HNO2, H2SO3, HBr, H2CO3, or H3PO4. As we just said, it's something that fully dissolves. HBr does because it's a halogen that's not fluorine connected to the hydrogen. Why that is, again, you'll learn later, I think. It has to do with stability of the ions, right? That form. 17, it says 12.5 milliliters of 0.28 molar HNO3 and 5 milliliters of 0.92 molar KOH are mixed. Is the resulting solution acidic, basic, or neutral? So you need to figure out, so these are strong acids and strong bases, right? So we have to figure out which one we have more moles of. To be more precise, we have to figure out if we have more moles of H plus or more moles of OH minus. Why am I saying it like that? Because what if you have a compound where you have two hydroxides or two hydrogens, right? So we need to figure out which one's more, H plus or OH minus. So I'm going to convert the nitric acid first. The moles. I have 12.5, which is 0.0125 liters of solution. And I have moles of HNO3. For every 1 mole of HNO3, it gives off one proton or one hydrogen. And then we're going to get a number. Moles of hydrogen. So that's how many H plus we have. And that should be hydrogen, protons. It's not deprotonated. Protons. We have that many moles of H plus. Then we can go ahead and do the same for KOH. Zero was 0.005 liters. Mole. So then we're looking at moles of hydroxide. So you get for every 1 mole of KOH, you produce 1 mole of hydroxide when it dissolves. There's only one hydroxide in there. And then you get 0.0046. So we have more moles of OH minus than we do of H plus, which means when they react, there's excess OH minus, which means the solution is basic. And we're done. The answer is B. 18 is what volume of 0.110 molar H2SO4 is required to exactly neutralize 10 milliliters of 0.085 molar NaOH. Okay. So we're doing the same thing here, right? Kind of as before. So we know how much NaOH we want to neutralize. So let's figure out how many moles of NaOH we need to neutralize. So we start with 0.085 moles per liter of NaOH. We have 10 milliliters of NaOH, 0.01 liters. So now we're working in moles of sodium hydroxide. So I need to have an equimolar amount of sodium hydroxide to H plus protons that are produced from H2SO4. Notice how I said H2 protons. I didn't say equimolar amount of H2SO4 and NaOH. Why? Because if you write the equation out, you can see that we use two NaOHs for every one H2SO4. So what do? We use stoichiometry for every 2 moles of NaOH. I need 1 mole of H2SO4. How do I know that was the equation? Because hydroxide reacts with the water. That's always going to happen in your acid-base reaction. Hydroxide reacts with the hydrogen to form water. There's 1 hydroxide in sodium hydroxide. There's 2 hydrogens in every sulfuric acid. So you need twice as many sodium hydroxides. Now we're working in moles of sodium hydroxide. And we want volume. So what we can do is divide by our molarity. Another way to do it that may make more sense is finding this, plugging into this, and then you can solve for the liters or the volume, right? Because that's now moles divided by molarity, right? Just from algebra. And then we get the answer of 3.9 milliliters. Oh, wait, this is in liters. So if we wanted in milliliters, sorry, then we convert to milliliters. So 1 liter, 1,000 milliliters. Then we get 3.9 milliliters. And the answer is D. Moving on, we have 19, define oxidizing agent and reducing agent. So you've probably learned redox reactions if you're watching this. So what is an oxidizing agent? What is a reducing agent? Well, we talked about what is reduction, what is oxidation. So when you have a chemical reaction where you're transferring electrons around, this is what we call a redox reaction, where you have a transfer of electrons from one type of atom or one type of molecule or ion, whatever, right, to another. That is a redox reaction. So if you're gaining electrons, you have a reduction in charge, right? So if you're being reduced, you're gaining electrons. If you're being oxidized, it's the opposite. You're losing electrons. Now, the oxidizing agent is the thing that is the thing that's being reduced. So the oxidizing agent is the molecule being reduced, which causes oxidation of the other thing. Similarly, the reducing agent is the molecule being oxidized, which reduces the other species. So it's what it's doing to something else, not what's happening to it, but they are related, right? They are related to one another. 20 says hydrogen peroxide is a versatile chemical. Its uses include bleaching, wood pulp, and fabrics, and substituting for chlorine in water purification. One reason for its versatility is that it can be either an oxidizing or a reducing agent. For the following reactions, identify whether hydrogen peroxide is an oxidizing or a reducing agent. So let's look at what's happening here. You see the iron. You're generally going to look at the metal thing. So you see the iron here. It goes from a 2 plus to a 3 plus, which means the iron is being oxidized because it's going up in charge. Because the iron is going up in charge, that means it's being oxidized, which means it's the reducing agent, or hydrogen peroxide is being reduced, which makes it the oxidizing agent. B, same thing. We're going to look at manganese. So Mn right now has a charge of +7. Each oxygen gives a -2. To get to -1, -8 +7 gives you -1. It goes from +7 to a +2. So Mn is reduced. Because Mn is reduced, that means that the other thing must be the reducing agent. So H2O2 is the reducing agent and it's being oxidized. One thing is always going to be the oxidizing agent. One thing, the other one's going to be the reducing agent. One thing will always be oxidized, the other will always be reduced. So if you know what one is, you know the other has to be the other one, right? One's being reduced, the other has to be oxidized. 21 says, given the following equation, MnO4, aqueous MnO4 plus I minus gives Mn2 plus I2. Fill in the following table of oxidation states for each of the elements in the products and reactions. Element Mn, oxidation state of the element in the reactants, oxidation state of the element in the products. So this is what I just did a second ago. So Mn in this starts off at a +7. Again, if you need to review oxidation states, I think check worksheet number 2. Oxidation state of the element in the products. This is a 2 plus or +2. Then we have I. So I goes from a -1, as you can clearly see, and then it goes to 0. When it's diatomic, you assume it's 0. They're equally sharing. And then O. O goes from what we assume is a 2 minus, and it disappears. What the heck? So I think there was an error here. It's usually gonna end with a 2 minus. Um, yeah, the O disappeared. Um, Not sure about that. That's not the correct equation, obviously from the law of conservation of mass, but O typically is going to stay the same. What is oxidized? What is reduced? So what is oxidized is I minus, right? I minus is going up in charge. So it's a thing being oxidized. Mn is the thing being reduced. What is the reducing agent? It's the thing being oxidized. So that's I minus. The oxidizing agent is the thing being reduced. And it says balance the reduction half reaction in acidic solution, the oxidation in acidic, and then give the overall reaction. So we're going to look at the half reaction first. So the thing that is being reduced, right, which is manganese. So the thing that we start with first is an MnO4 minus. Then I'm going to leave some space because I'm going to add some stuff on the left. And then I know it turns into Mn2 plus. Okay. So the first thing I want to figure out, well, there's actually a few things here. So the first thing is how many electrons get transferred over, right? Well, we know how many electrons get transferred over from over here, right? Manganese charge goes down by 5, which means that it must have gained 5 electrons. So if it gained 5 electrons, the electrons have to be on the reactant side, right? They come out on the product side, they're being given away. If they're on the reactant side with the atom, then they're being kind of taken in by the atom. So I have 5 electrons there. The next thing that you have to make sure that you do is balance out the oxygens. So how do you balance out oxygens? And this is always going to be the same for any half reaction. Whether it's an acidic or basic, we'll talk about how you do basic, but treat everything like it's acidic at first. And then at the very end, there's just one extra thing you have to do for a basic solution. So an acidic solution, write the reduction half reaction like this. The thing being reduced is the reduction half reaction. We balance the electrons. We balance the oxygens using water. There has to be 4 waters because I need 4 oxygens on the right. And then we balance the protons, which is 8H plus, like that. And you're always going to do it in the form of H plus to balance that. The next one is we're doing the oxidation half reaction. So the oxidation half reaction is iodine is being oxidized. And then it turns to I2 and it gives away 2 electrons. Great. So now what you have to do, so from adding equations before, right? We think we saw it in the previous worksheet where you were adding different equations. These are called half reactions because they make up half of the redox reaction. 2 halves make 1 whole. So you're going to have to add these equations. When you add these equations, you want these equations to have the electrons. That's the important part. The electrons have to cancel out. So I have 5 electrons on the left here. I'm going to add it with this one, 2 electrons on the right. And I'm going to add these. Now, for the electrons to cancel out, they have to be the same integer coefficient on the both sides, right? So this is 5, this is 2. Those are clearly not the same. So to make them the same, what I'm going to do is find the least common multiple. Least common multiple of 5 and 2. So this is like with fractions, that you've seen in algebra. So adding like 1/3 to 1/4, the least common multiple is 12. You make them both out of 12 and you add them up. In this case, we're finding the least common multiple, so they cancel out. So the least common multiple is 10. So I'm going to multiply the top one by 5, or 2, sorry, by 2 to get 2MnO4 minus plus 16H plus 10E minus yields 2Mn2 plus 8H2O. And then the next one I multiply by 5. So I get 10I minus, yields 5I2 plus 10E minus. And now you see that the electrons are balanced if I were to add these 2 equations, 10 and 10, right? This is to balance the electrons when adding half reactions. Then it says give the overall reaction below. So we just go ahead and add these. It's actually as simple as that if you balance these correctly already. And then we have 2MnO4 plus 10I minus plus 16H plus yields 2Mn2 plus 8H2O plus 5I2, and it's done. All right, great. Now we can do the next. So again, first you have to figure out which thing is being reduced and which, and which thing is being oxidized. So 22A, this one, manganese is being reduced again. Manganese goes from a +7 to a +2. Goes from a +7 to a +2. And then the sulfur is what's being oxidized here. Right, so if we assume oxygen is a 2 minus, then we have -6 from the oxygens. Then this is -2. So we have to have +4 from the sulfurs. So that should be a +2. And it's going from a +2 to, let's see. So this is -8 from the oxygens. You need a +6 to make up the deficit. So it goes from +2 to +6. Oh, wait. No, that's correct. Yeah, +4, and you split it up. So it goes from a +2 to a +6. So the reduction half reactions. First, we start with MnO4. I know it's going to turn into Mn2 plus from my product over here. I balance the waters first. Like so. Or I balance the oxygens using water. My bad. Misspoke. I balance the electrons, and then I balance the hydrogen. So it's the exact same as we saw above. Then we have the oxidation half reaction. So we have S2O3, 2 minus. Leave some space. This turns into SO4, 2 minus. So I'm going to balance the charges first. So sulfur goes from a +2 to a +6. And actually, let me do one thing first. Make sure you balance out the non-oxygen elements first. So in this case, we have to balance the sulfur, right? Great. So we have a 2 minus overall on the left, 2 minus on the right. Again, we're looking at the oxidation state of sulfur. So each sulfur goes from a +2 to a +6. So that means we need 8 electrons because there's 2 sulfurs, right? So just to recap, sulfur went from a +2 to a +6. Each sulfur needs 4 electrons, or lose 4 electrons. My bad. Wrong side. Each sulfur needs to give away 4 electrons. So we have 8 electrons in total. Then we go ahead and balance out whatever else we need to. So in this case, we have the oxygens. We have one less, or we have, yeah, quite a few less oxygens on the left. So balance that with water. There's 8 on the left. Now we have 8 on the, sorry, there's 8 on the right. Now we have 8 on the left by adding 5 waters. Then we go ahead and balance the hydrogens. So there's 10. And then we look for the least common multiple. The least common multiple of 8 and 5 for these electrons to cancel out is going to be 40. 5 and 8 to cancel out all these electrons is 40. So I need to multiply the top one by 8 and the bottom one by 5. So least common multiple of 5 and 8 is 40. Now we go ahead and add these up. We have 8MnO4 minus, right, and I'm doing the multiplication at the same time, plus 64H plus, and then the electrons will cancel out, so I'm not going to write that in, plus 5S2O3, 2 minus, plus 25H2O yields 8Mn2 plus 32H2O plus 10SO4 2 minus plus 20H plus. Now we can go ahead and start canceling things out. So I see I have 20 H pluses on the, oops, that should say 50, not 20, multiplied by 2, 50 H plus. Let's double check our math. 8Mn2, 8 times 4 is 32. That's 10, that's 50. And the electrons cancel out. That's good. So 50 H plus cancels out. That turns to 14. Then we also have the waters. So the waters cancel out on the left. There's more on the right. That turns into 7. And then we go ahead and write our final simplified equation. Oops, and I forgot the hydrogens. That's it. That is your answer, and that's how we get it. All right, last problem of the worksheet. It says in a basic solution, we have silver, chromium, or chromium something oxide yields silver ion plus chromium hydroxide. So we're going to treat this the same at first as a like an acidic solution. And then there's just one step at the end that you have to change. Everything else is the same though. I'm also going to get rid of this so I have more space. All right. So the oxidation half reaction is silver because it's going up in charge. It's neutral at first, and then it goes up in charge. Great. To balance the electrons, there should be one electron on the left. Then that's it. Nothing else to balance here. And then we get to do the reduction. So we go from CrO4 2 minus, leave some space here, CrOH3. All right. Now we have to figure out what the oxidation state of chromium is. So chromium goes from, I'll write it over here. So Ag is oxidized. Cr is reduced because it goes from a +6. Since there's 4 oxygens, those give a -8. And then it's 2 minus, so you need a +6. And then there's 1 chromium. And then it goes from +6 to +3. Each hydroxide is a +1 or -1, sorry. So you need a +3. So since there's 1 chromium, we're going to add 3 electrons on the left to balance this out. Great. Because it gains 3 electrons, each chromium gains 3 electrons, and there's only 1. And then we get to balance everything. Very fun. So we have water on the right, then we balance with protons on the left, like so. So we have 4 waters on the right and the left. Then we have 5 H's on the right and none on the left. So we put a 5 here. The basic part we will finish at the very end. So now we add these equations. The least common multiple is 5. And we add them up. So this is going to be 5Ag plus CrO4 2 minus. The electrons cancel out because, again, oh, wait, it's 3. Oops, that should say 3. My bad. Sorry, long video. 3Ag. 3Ag plus CrO4. So now the electrons cancel out properly. 3 on the right from Ag. 3 on the left from the chromium. Plus 5H plus yields 3Ag plus CrOH3 plus H2O. Now this is not correct because this is an acidic solution. So how do you change it to basic? Well, to do the last step, we're going to neutralize the OH, or sorry, H plus on whatever side it's on. So on the left side here with OH. So we're going to add OH to both sides equal to number of H plus. And then this is to make it basic. Now we go ahead and do this. So if I add H plus or OH, sorry, to both sides, plus 5 OH minus to both sides, then I get 3Ag plus CrO4 2 minus plus 5H2O yields 3Ag plus CrOH3 plus H2O plus 5OH minus. Now you can see I have no protons. Now we have to cancel out the water. There's only one thing to cancel out here, that, right? So this goes to a 4. Then our final answer, 3Ag plus CrO4 2 minus plus 4H2O yields 3Ag plus CrOH3 plus 5OH minus. And there we go. And it is done. So I hope that video helps. I think the most difficulty people usually have is with the redox reaction stuff. So hopefully that helps in terms of how do you do it? How do you balance it? What's the procedure if you want a really clear method? First, write your reduction and oxidation half reactions, balance any non-oxygen or hydrogen atoms, then balance oxygen using water, then balance hydrogen using protons for both half reactions. Multiply each half reaction by the number to make the electrons cancel out. So like what we did here, add them up, cancel things appropriately. If you're in acidic solution, you're done. If you're in basic solution, add OHs to both sides until the H pluses cancel out. So 5 in this case. And then, yeah, add the H pluses to OHs, they form water. And then you're done. All right. So I hope that helps. I'll see you in the next video or in discussion.